Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to focus in on the pH and how the pH can influence our molecules. Okay, so that's what we're going to do. At this point, we've learned about the Bronsted-Lowry and Lewis definitions of acid-base. We've also done a lot of practice within these two topics on how to do various things, right? So how to determine the acidity of a molecule, how to use pKa values to figure things out as well. In this video, it's all about the solution and what influences a solution can have to our molecules. This is a very important step in our direction towards mastering organic chemistry, because pretty much most of what we're going to learn about in organic chemistry, not everything, but a lot of it takes place in aqueous environments. Okay, so let's get started. Let's take a look. The first thing I want to point out is, what is a pH? Well, the pH is the measure of the acidity of the solution, not the molecule. So molecules have pKa values. That is the acidity of the actual molecule itself. But the solution that it's in can also be considered acidic, and this is how we measure it. We use the pH. So I want to point out that, again, pH allows us to determine the acidity of a solution, and that it ranges from 0 to 14. Now, it's important to note that just like pKa, pH is derived through a log, right? So that means that pH is an exponential value, right? So it's the log of the concentration, a negative log of the concentration of acid. That's how we get the pH. So what this actually means is that the greater the pH is, the higher that number is, closer to 14, the more basic the solution is. Whereas the lower the pH is, then the more acidic the solution is. Okay, so this is something you have to keep in mind. Now, when I say acidic and basic, what am I referring to? Well, what I'm talking about is the use of either H3O plus or hydroxide. Remember, aqueous solution is water, and the acid form of water is H3O plus. The base form of water is hydroxide. So if we have an increase, well, actually I should switch this up. So let me put this one over here. So if we have a high pH, that means we have an excess of hydroxides. So that would mean we have more hydroxides in our environment. Okay? Whereas a low pH means we have an increase in hydronium, H3O plus. Now, when you have a weak acid and base combination, so a weak acid and its conjugate base, for example, well, what that does is it creates a buffer environment. So let me remind us what that is. What is a buffer? A buffer is when you have a weak acid and conjugate base inside an aqueous environment. Now, it has to be weak, because if it was strong, if it was a strong acid, it would completely dissociate in water. And so that wouldn't help us, because we need to have acid and base around in order to act as a buffer. So what does it actually do? A buffer maintains a pH. So if the solution becomes too acidic, the buffer kicks in and starts to deprotonate the solution. If the solution becomes too basic, the buffer kicks in. The acidic molecule starts to protonate the solution and bring down the pH. So it shifts, it monitors, regulates the pH of our environment. That's what a buffer does. And again, it's a weak acid-base combination that does this. You can't use a strong acid-base. It won't act as a buffer. Now, these are very powerful ideas, because it allows us, again, to keep a monitoring effect on our pH. But we're talking about things right now from the solution point of view, from water's point of view, from the aqueous point of view. But what about the molecule's point of view? That's what we're going to focus our attention on now. So we're going to answer the question as to, what does this mean for the molecules in the solution? When a molecule in a solution is acting as a buffer, what does that actually mean to the molecule? Okay, so let's take a look. So the first thing is, I want to remind us that if we have a solution of water, so here's H2O, then what we're really doing is increasing or decreasing the concentrations of hydroxide or hydronium. But in order to keep a constant pH, we have to offset those changes with our molecular buffer, our molecules that are going to act as buffers, okay, in our solution, that is, okay? So imagine if we have hydroxide and we have hydronium, right? We have these two. And of course, water. This is in water. Now, if we have an increase in hydroxide in our environment, what is that doing to the pH? Well, it's raising the pH, right? The more basic the solution, the higher the pH. So if we have a molecule, let's say we have a molecule Z, and it's in its acid and Z in its base form, right? So we have these two molecules here in its acid and base form. They're conjugates of each other. They're weak acid and base combination, right? So they're not, it's a weak acid, that is. So these two here are monitoring the solution. If we start to add a lot of hydroxide into the solution and the pH starts to rise, then the acid form of this buffer is going to start protonating those hydroxides. So if we start dropping in hydroxide and it goes in, well, then our acid is going to be kicked into gear and it's going to start to protonate those hydroxides because we don't want to increase the pH. We want to keep it level at the same level, right? So we have to start bringing it back down. And so that's how we do that. We disable those hydroxides by turning them into water. Okay, now what happens if the opposite? What if instead we have H3O plus and we start throwing that into the solution? Now we have a more acidic, so we're lowering the pH, we're making it more acidic, and so all of a sudden the base part of our buffer system is going to kick in. And it's going to start to pull the H's off of those hydroniums. It's going to start deprotonating them to go back to water and bring back up that pH, right? So this is the basic mechanism for how a buffer works. Okay, so now we're starting to get a better sense of how the molecules are engaging in this environment. Okay, and so we're going to come up with some standard rules based on this analysis that I just gave you. This analogy here, I guess this example here, right? So in order to do that, let's first come up with something that relates the pKa of our molecule, the acidity of our molecule, to the acidity of the solution. And actually, let me write this down. So pKa equals the acidity of molecules. And the pH equals the acidity, or the measure of acidity, of the solution. That's the difference. We use different terms to measure the different components of our environment. That's what we're seeing here. So let's go back and think about this now. We have this idea. We know that Z, H, and Z is our buffer molecules. Those are our acid and conjugate base forms. Okay, so how does this work? Well, the pH is equal to the pKa, the acidity of our molecule, right? Remember, by the way, this is an exponential value. Here's exponential, there's exponential. These are all exponents. Okay, and so the log is also going to give us an exponent as well. So this is all equaling exponential value. So it's the pKa plus the log of our ratio, our base to acid ratio. So our base to acid ratio. That's what we're looking at here. And so what we do is we start with the pH and the pKa equal to each other, for example. And now if we do some modification to our concentrations of acid and base, we're going to either increase or decrease our pH because we're going to add more or subtract from the pK value that we're starting with. And that's how we get the pH. So let's take a look at this a little bit more closely. Now, first thing I want to do is I want to review a very simple, and I know this is simple, but I want you to connect with this. And the reason why, let me just preface this. You really need to know this for the whole year. And, you know, as you go on, you're not going to be thinking about what pH means or pK means.